This is lecture 23 of condensed matter physics 1. And in the past 2 or 3 lectures, we have been discussing crystal binding. So, what I am going to do today is solve 2 or 3 problems based on whatever we have done in lecture 21 and 22, and then describe some other bindings in crystals for which I cannot do any analytical calculation here. So, we will just describe them briefly qualitatively. So, to start the problems, let me just recall that we had done noble gas solids, in which we took the potential between, or the energy between 2 atoms as 4 epsilon times sigma over r raised to 12 minus sigma over r raised to 6, and this is known as Lennard-Jones potential, with epsilon and sigma being parameters of the potential, and they depend on the system. That is, they will be different for helium, neon, argon, and so on. And then we calculated the total energy by summing over the pairs. So, this was equal to summation I j, I not equal to j, this is u r I j, and this, there is a factor of half here. This then came out to be n by 2 summation over j, j not equal to 0, u r I j. So, this is the way we calculated the energy, and then we wrote this as equal to n by 2 some alpha times this is different for this. So, let me just write this. This was written as sigma over r, let me write capital R raised to 12 some summation j 1 over p I j raised to 12 minus sigma over r raised to 6 summation over j 1 over p I j raised to 6, where r is the nearest neighbor distance, and these sums, which I called B12 and A6, are calculated using a computer. The sums are calculated once and for all, and then you can calculate the energy. This was noble gas atoms. The other system we dealt with were ionic crystals, and in these we had alternate positive and negative ions, and the energy between two ions at distance r was given as one short range part repulsive potential, and then one attractive Coulombic potential. And you can write the short range part as an exponential. So, this was written as some lambda e raised to minus r over rho, where rho and lambda are the parameters, and minus some e square over 4 pi epsilon 0, where I am assuming there is this electronic charge on the system 1 over r. This should be small r. So, let me correct that. This is small r. And then when you summed over all the pairs, so E total was equal to summation over all these pairs of this u r I j, and this is over 2 n ions, or equivalent to n molecules. I am assuming there are 2 ions in the molecule, and this came out to be n summation the short range part was only over nearest neighbors, and I had asked you why that can be done. And then there was this minus summation 1 over p I j 1 over r e square over 4 pi epsilon 0. And the second part we wrote as, so this was equal to n z lambda e raised to minus r over rho, that was the nearest neighbor, minus alpha e square over 4 pi epsilon 0 r, where alpha is known as the Madelung constant, and its sum over this plus minus 1 over p I j. Again, it is given of course by calculation for different kinds of structures. So, based on these two, I am going to now solve some problems. Problem 1, this is taken from Kittel, and it says, using Lennard-Jones potential, calculate the ratio of cohesive energies of neon in the BCC and FCC structures. Okay. So, what are we doing in this problem? We are taking the neon crystal once we are making it arbitrarily, or imagining that this could be a BCC crystal, and the other structure we are considering is the FCC structure. And the other atoms are on these faces. Already in lecture 21, I have given you the lattice sums. So, in lecture 21, we had calculated B12 for BCC. I had given you the number and you will be calculating it, which is nothing but summation over 1 over p I j raised to 12, sum over j, j not equal to 0. This comes out to be 9.11. And B12 for FCC came out to be 12.13. Similarly, A6 for BCC. So, we are summing over all these atoms in a BCC structure, which is nothing but summation over j, j not equal to 0, 1 over p I j raised to 6. This came out to be 12.25, and A6 for FCC was 14.45. So, we know all these structures and we can calculate the energy. E by n, as I have just reviewed and you also recall from previous lectures, E by n is given as 2 epsilon B12 sigma over r raised to 12 minus A6 sigma over r raised to 6. This is with respect to r. So, minimum of E by n occurs at, and we had calculated that. So, I am going to call that r 0, which is r for minimum, and this comes out to be 2 times B12 over A6 raised to 1/6. So, depending on what B12 and A6 are, R naught is going to be different. So, this gives you, if you do the calculation, this gives you R naught equals 1.068 sigma for BCC, and R naught is equal to 1.09 sigma for FCC. Question here: why is R naught FCC greater than R naught BCC? Argue qualitatively. What feeling do you get? Why should R naught for FCC be larger? That means there is some more repulsion or whatever, right? So argue that. Okay. Once we have gotten that, then it is very easy to calculate that E by n BCC divided by E by n FCC comes out to be 9.11 sigma over r raised to 12 minus 12.25 sigma over r raised to 6, and this is for BCC, divided by 12.13 sigma over r raised to 12 minus 14.45 sigma over r raised to 6, and this is calculated for FCC. We have gotten sigma over R and all that. So, you plug in the numbers and you get your answer to be 0.957. So, what you see is that energy, or cohesive energy, in BCC structure is only about 4% higher than that in FCC. Nonetheless, that is enough to favor FCC structure, and this is all at 0 degrees temperatures, and also we have neglected any quantum corrections that you should keep in mind. Okay, so that is that. Problem 2. This is also from Kittel, and it says calculate the cohesive energy, and this is to be calculated with respect to free ions. And when I say with respect to free ions, that means I am not really taking into account the ionization potential and electron affinity. I am just taking this crystal and just separating it into ions of KCl, which is obviously K plus plus Cl minus, in cubic zinc sulfide structure. It is given that, and again this is taken from some experimentation, Z lambda is equal to 2.05 times 10 raised to minus 8 ergs, and rho equals for this is this many ergs, because this is Z. So, we are talking about a particular structure where the nearest neighbors are known. So, this is for NaCl structure, and again rho is determined from KCl ion. So, rho is equal to 0.326 angstrom for KCl. So, what we are doing now is that we are taking the KCl solid and separating it into K plus and Cl minus ions. That is what we mean by with respect to free ions. In the NaCl structure, we have the big ions here, and as I had said once earlier while discussing crystal structure, potassium and chlorine ions are almost of the same size, and then we have these other ions sitting right here alternatively. Then this huge ion is also right here in the middle, and then you have small ion here, and then the huge ion right here, huge ion right here, huge ion right here on this side, and there is a small ion right here in the middle, and so on. All right. So, you can see that there is a big ion on the back side also here, This is NaCl structure. Just look at the structure carefully. I may have missed one or two ions here and there, but what is clear is that if I look at the ion in the center, so I am just encircling it once more, it has 6 neighbors, 6 nearest neighbors. So, the value of z lambda that is you given, which is 6 lambda therefore, is equal to 2.05 times 10 raised to minus 8 ergs, implies that lambda, which is a property of KCl now, it is not in the structure, but KCl ion itself, is equal to 0.34 times 10 raised to minus 8 ergs. Knowing lambda is important because next when we consider the zinc sulfide structure, nearest neighbors are going to change. So, if I look at zinc sulfide structure of KCl, what we have is like the diamond structure, but shifted by 1/4. So, I am going to have one ion right here, then the rest are going to be FCC, and the other ion lattice is also FCC, but shifted by 1/4 along the body diagonal, and then this has its own lattice. There is one right here. So, this ion, red ion, has these 4 nearest neighbors at the tetrahedral site, and these are the nearest neighbors. So, Z, this is ZnS structure, and the number of nearest neighbors Z, small z, is equal to 4. So, Z lambda for ZnS structure is going to be 4 times 0.34, which is 1.36 times 10 raised to minus 8 ergs. So, we have gotten Z lambda for this. Now, recall that the energy per molecule per ionic pair is given as Z lambda e raised to minus r over rho minus alpha e square over 4 pi epsilon 0, where alpha is Madelung constant, which is equal to 1.75 for sodium chloride structure, and it is equal to 1.64 for ZnS structure. When you minimize the energy, the expression that you get for the minimum distance between the ions for R naught is distance between ions that give E minimum is determined by R naught square Z lambda over rho e raised to minus R naught over rho is equal to alpha e square over 4 pi epsilon 0, which I can write as, because I have to do that manipulation, I will write this as R naught over rho. I will write this whole thing in terms of R naught over rho. R naught over rho square e raised to minus R naught over rho is equal to alpha E square over 4 pi epsilon 0, and this I am dividing by Z lambda rho. On the right hand side, I have all known quantities, and the left hand side gives me R naught. So, solve for R naught. Now, before I do the calculation, I would like you to guess. So, make a guess whether R naught will be larger or smaller for ZNS structure in comparison to NaCl structure. And this is all being done for the same system, for KCl. So, if you look at this equation, R naught over rho square e raised to minus R naught over rho equals alpha E square over 4 pi epsilon 0 1 over Z lambda rho, and we will calculate this for R naught over rho. So, for NaCl structure, you have alpha equals 1.75. Now, all other quantities are fixed. So, E square and Z equals 6. All other quantities are fixed. E square over 4 pi epsilon naught is 2.56 times 10 raised to minus 38 times 9 times 10 raised to 9, and this comes out to be 2.30 times 10 raised to minus 28 joule meter. Only alpha and Z differ, and rho is given to be 0.326 angstrom. So, if you plug in these numbers, you get in this equation, you get R naught over rho square e raised to minus R naught over rho is equal to, for NaCl structure, this comes out to be 6 times 10 raised to minus 3. Keep in mind that left hand side is dimensionless, so right hand side is also dimensionless. Now, you got to solve it by trying, right? You plug in the numbers. This is a transcendental equation. So, from this you get R naught. This gives R naught equals 9.65 rho, which comes out to be 3.15 angstrom. So, for NaCl structure, R naught comes out to be 3.15 angstrom. Once you have gotten R naught, you can calculate the energy. So, E by N is equal to let's calculate this, 1.14 with a minus sign times 10 raised to minus 18 joules, or minus 7.15 eV. Now, you go to zinc selenide structure. For which alpha is 1.0 6, 4 and Z is 4 that we had already said. So, you plug in the numbers and you get R naught over rho square e raised to minus R naught over rho equals 8.52 times 10 raised to minus 3. So, right hand side is larger than for sodium chloride structure, and you solve it and you get R naught equals 9.2 rho, which comes out to be 3 angstrom. So, I am answering that question I asked earlier. R naught for zinc selenide structure is smaller than that for NaCl structure. If you did not think about this question earlier, think now, why should that happen? In any case, you have gotten that, and therefore, the energy E by N for zinc selenide structure comes out to be minus 1.12 times 10 raised to minus 18 joules, which is minus 7 eV. So, cohesive energy, and this is only ion energy, right? We have not taken into account the ionization potential or electron affinity. So, cohesive energy with respect to free ions is about 7 and 7.5 eV. So, about 2% more positive for zinc selenide structure than for NaCl structure. So, KCl is going to be found in NaCl structure, but the energy differences again you see are very small. Now, I have been saying that I am doing this calculation with respect to free ions. In the next problem, I am going to take that also into account and see what happens. So, the next problem I am going to solve is the cohesive energy of a sodium chloride crystal is 6 eV per NaCl pair. We had just calculated it to be minus 7.15 in the previous problem, now it is 6 eV, and that is the effect of ionization potential and electron affinity. So, we are going to give that information next. The ionization potential for sodium is about 5 electron volts, and electron affinity for chlorine is about 3.75 eV. And what we are going to ask now is, neglecting the repulsive energy, estimate the inter-ionic, that means distance between Na plus and Cl minus distance. Okay. So, if you neglect the repulsive energy, right. So, if we neglect the repulsive energy, then the ionic energy E by n per molecule per pair is going to be minus alpha E square over 4 pi epsilon naught r, the interatomic spacing. This is only with the ions. So, the total energy gained when forming a crystal from sodium and chlorine atoms is, so let us see, all negative is going to be gain. So, I have minus E square over 4 pi epsilon naught r times alpha is the energy gained when these ions come together and form this lattice. Then I had to give in I, the ionization potential energy, to ionize sodium, and I gained the electron affinity energy when I made the Cl minus ion, because when that electron goes in there, it releases energy, and that is known as electron affinity, and this is given to be minus 6 electron volts. So, what we have is that E by n, which is minus alpha E square over 4 pi epsilon naught r plus I, which is 5 eV roughly, minus A, which is 3.75 eV, is equal to 6 eV. So, you take things around and then you get alpha E square over 4 pi epsilon naught r is equal to 7.25 eV. And from this you can easily calculate r, and this gives you r to be 3.59 times 10 raised to minus 10 meters, which is 0.36 nanometers. So, that is the kind of distance, interatomic distance, that we are getting without repulsion. Now, when repulsion comes, we saw in the previous problem the distance comes out to be about 0.31 nanometers. So, again you got to think about why, when you are getting the repulsion, you are reducing the distance between the ions. So, these are the problems that I have done now based on the cohesive energy calculations of noble gas solids and ionic solids. Related solids, other kind of bindings that take place in crystals, and which we cannot be very quantitative here, are the covalent bonding, metallic bonding, and hydrogen bonding. These are the kind of bonds that are formed in a crystal, and the ones that we have discussed are called van der Waals bonding. This was Raynaud-Jones potential, and ionic bonding. So, what we want to do is look at these other kind of crystals and compare their strength, their bonding strength, their cohesive energies compared to these other crystals that we have already studied. So, let us start with covalent bonding. And you have learned covalent bonding in your previous classes. So, what this is sharing of electrons. Between atoms, and they form bonds. Here the specific examples that you have seen are diamond, even in silicon the bonding is the same, germanium the bonding is the same, and so on. So, I will focus on these examples. So, what this is number one, highly directional. And 2 is the strength of the bond is less than ionic bonds. Ionic are the strongest bonding that can take place. This is Coulombic attraction, but it can approach as it can become as strong as ionic bonds. So, approaches the strength of ionic bond. For example, a diamond is very hard, right. So, that carbon-carbon bond is very strong there. So, in this case, for example, if I look at the diamond structure, and we had been discussing it quite a lot, it is these carbon atoms sitting at face centered lattice, and then there is something shifted along the diagonal. So, we have the other lattice which is shifted along the diagonal by 1/4 the diagonal distance. So, all these atoms have this shifted atoms, and as I said in zinc blende structure, this atom red one is going to have the nearest neighbors, which are 4, and actually where it is sitting is, if you look at it carefully, the red atom sits at the center of a cube. Let me make this 2 body diagonals. This should not be the yeah, this is fine, and then we have this sitting at the center, and the other atoms are sitting at these ends of these diagonals. And this reminds you of sp3 hybridization, and you can calculate the angle between these. And this is the kind of structure that each atom in this diamond cell has, and these are covalent bonds. These bonds out here, highly directional covalent bonds. They are also the bond between CH bonds and CH4. So, these are covalent bonds. What I will give you an exercise here is calculate the angle between the bonds. And you recall from previous lectures that the packing fraction in this diamond structure is roughly about 1/3, 0.34. So, there are a lot of empty space in this. Nonetheless, the bonds are very strong. So, this is a kind of brief description of covalent bonding, directional, very strong, approaches as strong as ionic bonds, right. The other kind of bonding I want to discuss now is metallic bonding, And again, I mean in covalent bonding also, if you want to do the number game, you have to actually do a quantum mechanical calculation. Similarly, in metallic bonding, what is happening here is you have these ions like lithium plus, sodium plus or others, and in this these electrons have become delocalized. They are going all over the place. And in the sea of electrons, right, so let me make the sea of electrons. You have these ions which are sitting here. And whatever the energy difference is between free atoms and the energy of these systems here, the bonded systems, is the cohesive energy. Again, you cannot calculate the cohesive energy very easily. A full quantum mechanical calculation has to be done. But let us just make a rough estimate. So, if I were to estimate the energy of metallic crystal, what all does it have? It has kinetic energy of electrons, which is roughly 3/5 epsilon f per electron. And if you recall the numbers from our earlier lectures, this will be of the order of, let us say, 2 to 5 eV. Then you have energy of interaction, between the ion and the sea of electrons. So, what I can assume is that here is this ion and is surrounded by exactly the same amount of charge. So, 1 electron charge in a sphere of RsA0. We had already introduced this. So, if I assume the uniform charge density, this energy of the ion is going to be roughly 3/2 minus 3/2 E square over 4 pi epsilon 0 r. R is the radius, so minus 1.5 E square over 4 pi epsilon naught Rs A0. A0 is the Bohr radius. And to this, I will add Coulomb energy of electronic density, because after all this electron I am taking to be smeared around this, and this comes out to be 3/5 E square over 4 pi epsilon naught A naught Rs. You add these two terms, that gives you Coulomb energy. So, this is the kind of, I am giving you a rough estimate, an idea of how you can get this energy. Then you have to add something called the exchange energy, right. So, you add these terms and you get an idea about metallic bonding, right, how much, but the real numbers come from the calculations that have to be performed on a computer. These are quantum mechanical calculations where you have to solve the Schrodinger equation with these interacting electrons. But this can give you an estimate of this. So, next term is something called the exchange energy. This also comes from Coulomb interaction between electrons, and this also goes as 1 over Rs A0. So, you combine all this and you get the energy, right. So, finally, I will just give a comment on this metallic bonding. This is less strong than covalent bonding, and you can see, I mean, you can't really assign any direction to it, right, and it comes from delocalization of electrons. Sometimes people say that delocalization is actually reduces the kinetic energy, and therefore metallic bond is you know, the system binds. It's not just kinetic energy, as I just showed you that kinetic energy is of the order of eV. It's also the interaction between electron and the core, between electrons. So it's just many things there, right. So this is more involved than very simple minded numbers. Okay. And finally, I am going to discuss something called the hydrogen bonding. And most prevalent is in water, ice crystals. And what it involves is, this is Coulomb interaction between charges. You may wonder how Coulomb interaction come between charges when these systems are neutral, right. So I'll just show it to you, and this is not dipole or induced dipole. Induced dipole interaction like in Leonard-Jones. It's not that. That gives you 1 over r raised to 6 dependence. This is stronger. So just to give you numbers, Leonard-Jones epsilon was of the order of 1 over 100 eV. The hydrogen bond is of the order of 1/10 of an eV. So it's about 10 times stronger. And how it comes about is, if I have a system and let us say it has certain subsystems that have different electronegativities, then what would happen is that these charges, electrons would tend to be going away from somewhere and will accumulate in certain different regions. Maybe this has nothing. You could say this forms a dipole, but also, I mean, the charges could come, you know, a little far away, and then they can interact. So, for example, in hydrogen you have 2 H and 1 oxygen. Their electronegativities are different. So, what happens is that one of the systems, oxygen, ends up getting little negatively charged and these positively charged. If I get another water molecule here, this will flip and you would get positive charge on the upper side, negative on the other side, and these charges will interact. If you think of this as dipole, these are permanent dipoles. Then the energy of interaction will be proportional to 1 over r cubed. And Leonard-Jones was induced dipoles, and this was proportional to 1 over r raised to 6. So, this makes it stronger. So, the various ways of looking at it, a system has elements that have different electronegativities and charges separate out, and those charges interact and give you the hydrogen bond. So, hydrogen bond comes from interaction between charges, you can say partial charges, separated in a system with components that have different electronegativities. Now, you know that halogen systems have very large electronegativity. So, systems or molecules that have halogen atoms in them would tend to make the hydrogen bond with other similar systems. So, these are three other bindings that I have described qualitatively, and as I have said 2 or 3 times, real numbers come from true quantum mechanical calculation. So, let me now conclude this lecture. One, we did some problems on cohesive energy of noble gas solids and ionic solids. And then we discussed qualitatively a metallic, covalent, and hydrogen bonding. Thank you.